homework up there this week, so you were free. But today we're going to start on Fourier transforms. First, before I do, or Fourier series analysis, before I do, does anybody have any questions about anything we've covered so far with Laplace? Yes?
Can you go over the quiz?
Yeah, sure. Which problem?
The quiz B problem.
Can you tell me what it is?
No.
Does anybody have quiz B available?
I don't think you posted it. Yeah, you haven't posted the solutions.
I'm sorry, I will do that. The quizzes are outside my office. If you got, how many got there?
Oh, that's right. I have one. Let me
You
grab
got
it.
yours, didn't you?
I did, but it's in another bag.
Well,
I have mine. Was it A you were looking for or B?
I would.
They're very similar.
A.
They're like the same thing. You could get them on
Here,
there.
these are just right out of the homework. So what's it called? Mark? You don't make it like they used to. All right, here's what they are. You can keep that.
I did not know that.
It doesn't matter which quiz you had. This is gonna be the V source. You're gonna have a resistor R here. Forget the value right now. This fed in to the negative terminal. This is the positive, that's grounded. Here, you had a capacitor and you had a resistor. I'm gonna label this R1, this R2, and this C, and this went to the output. And that's ground, plus the minus, V out. Now, what I first wanted was a transfer function for these. So that would be in the S domain. I wanted H of S. All right, that's what we're gonna get right now. Everybody follow me on this? This is a template problem. I'll tell you what the template's from, it's this. When you have some Z1, and I made sure I put this up here and gave you several problems with this, and you have Z2, and this is plus the minus, this is grounded, this is V out, and this is V in. Then H of S, which is V out over V in, is simply minus Z2 over Z1. Does everybody recall that? That's a very, this we went over many, many, many times, right? We can go through the analysis, but that's what it comes out to. And this is Z2. And I'll slow down, but this is something I think we all know. How many are familiar with that? This is something that is almost an automatic. You can get it from the analysis. If that's ground, that's zero. The current here is just VI over Z1. That current flows here. It develops a voltage plus to minus VI over Z1 times Z2. And the output voltage will be minus that, right? And you can get this very quickly. It's fairly obvious. Now, one thing I caution everybody about, if you try to jam all this information in Thursday night, you're probably gonna fumble it royally on Friday morning when you have a quiz. So make sure you spread it over time and you keep doing this. Every time you get a homework assignment, do it. You won't mess up then. So if I want this, the first thing I have to do is put the impedances in terms of the S domain. Here, the capacitor has an impedance of 1 over CS. The resistor is just R2, do you agree? Now, this entire thing, I'm gonna label just Z2 so you can see it. Z2 will be 1 over R2 plus SC, agreed? That's 1 over 1 of the first impedance plus 1 over the second impedance. And I do it this way because it doesn't have to be 2. I could put 3 here very easily. As a matter of fact, I will on a test probably. It will be an inductor, capacitor, and resistor. Then it's 1 over the first plus 1 over the second plus 1 over the third. Y'all understand that? Now if you just do the cross, if you say first impedance times second over first plus second, it works out the same, but there's a little more math involved. Everybody got this? So just leave that there as Z2. Now my transfer function is minus Z2 over Z1, which is R1. Do you all agree with that? Take a look and see. I have to make sure we all see this. I'm glad you asked this. Because I saw there were a lot of people that messed this up and it troubled me. There are plenty of 10s, but this was like a gimme. It was meant to be a there was nothing hard about this, is what I'm saying. There was nothing that you haven't seen. So now when I take a look at this, it's minus 1 over this, right? So over R1, so I have 1 over R1. Now I divide that by 1 over R2, right? Plus SC. Agreed, class? That's H of S. And now I'm going to clean it up a little so I can do an inverse Laplace transform. And when I do that, I need to go ahead and divide top and bottom by C. So now I have minus 1 over R1C, right? Then it's going to be times 1 over the quantity, and here it's going to be 1 over R2C plus S. Please take a look at that and convince yourself that's right. The same form happened on both tests, or both quizzes. It didn't matter if you had A or B, that's the form it came down. The values are different. Are you all with me? Now, if I do the inverse transform of this, if you just look at it for what it's worth, this is a simple scale factor. Does everybody agree with that? There's nothing but a scale factor there, correct? Like a constant. This is S plus a constant A, right? This transforms as a simple exponential decay times U of t. Do you all see this? So here, when I go, if I wanted H of t, that would be minus 1 over R1C times e to the minus, and it would be t, and it's going to be divided by this constant, which is divided by, or I'm sorry, divided by R2C times U of t. And that's how simple it was. And you could have done it many, many ways. You could go ahead and say that's 0, I get I1 equal to Vs over R1. Take that I1, multiply it by that impedance to get the voltage from here and here, make it a negative, and then divide by Vs. So it doesn't matter how you did it, the results should be identical to that. And you can plug in the values for R's, I don't remember what they were. The only thing you get is a different scale factor and a different constant for the two quizzes. Does everybody see this, class? I meant to be very fair about that. There was nothing I tried to do that was in any way, shape, or form tricky. It was a very easy quiz. And you did have several problems like this too. Any other questions? Does that answer yours? And if you wanted to put in, now this is going to evolve into more complicated problems, so here's something for a quiz, for a test. I might give this as a function. It might be like e to the minus 10t u of t, all right? Then you would have two poles that you would have to expand into partial fractions. Follow me? It could be a double pole. I mean, it could be a double pole, follow me? But that's the type of nature of the problems you get. Now, if I'm asking you to synthesize something, before I did that, I would probably give you some more drill problems on that, because synthesis, if you're going to do it, it requires a lot more, if you're going to actually build it with components, a lot more componental circuits, right? Every time you have that 1 over S thing, you have an op amp. Every time you have a multiplier R, you have an op amp, right? And then you have to have a summer, which is another op amp. So you can get a fairly busy drawing. That might be more of a homework project than it would be on a test. That'd take too long, unless it was a final exam. Got it on that, class? Are you with me? Can somebody just tell me what the problem was? There another test or something, or a basketball game? Well, I mean, I don't know why the class overall had a poorer performance on this than I expected.
I forgot how to do equivalent impedance, I think. Because I had 1 over
Is that right?
R2 plus 1 over SC, I think.
Yeah, I messed up my equivalent impedance, and then it just messed up my,
Yeah, that
I
just
did
messed
everything
up
else right, but it messed up my entire.
Here's a heads up, all right? Make sure you know how to do parallel and series impedances. That's an assumption I make, because if you come out of Erwin's class and you can't do that, God, Dave heard that, he would not be happy. It's something I assume you know how to do, because you've done it a billion times, probably, with those. Erwin gives a lot of homework, as I recall, and you must have seen it over and over and over, so it'd be second nature. But just stay sharp on that stuff. Any other questions before I get going? Now remember, the realization is something that's hard to do in an exam, except the final. But I am going to ask you that. I'm going to give you a project for that, just as a special credit or something, because realization is something, that's synthesis. Analysis is something that they take you through circuits in this course, and you're in the analysis mode. You're trying to analyze things, figure what output to input. But synthesis is where it's at. When you're out there as design engineers, you're going to build things. You're going to create or synthesize things based on need. And that's where that technique of synthesis is so important. And of course, I like high fidelity sound, so I personally like that because of a selfish interest, because now I can make my own filter, I'll call it an equalizer, that will do anything I want, so if I have dirt cheap speakers, they'll sound wonderful. And that's my selfish. Has anybody read about Bose yet with 901 speakers and how I made them? Read about Professor Bose at MIT if you want a story that will really give you some interest, create an interest in you for learning this stuff. Next, we get into, and I mean, if you have questions about the homework or quizzes, just ask them, and I'll try to address them. Next, we're going to do, this is Fourier series analysis. And this is a very, very important topic. And here's why. Laplace transforms are primarily used for synthesizing circuitry. In synthesizing, not analyzing. You can use them, but mainly synthesis. All right, does everybody understand? It solves differential equations, right? But its real power is synthesis. Fourier series analysis is all about figuring out what a waveform's energy or power content looks like, really power content, in the frequency domain. So first we assume we have a periodic signal. What that means, it's something that repeats itself over and over again, a sine wave, a square wave, something like that. It goes on forever. Technically, it means it has an infinite amount of power, but it has a finite amount, infinite amount of energy. It has a finite amount of power. Follow me? It's something that you're thinking about power, not energy with. When I assume that you got a periodic signal, like so, and I'm going to use x of t here, and it could be something like this. It could be, boom, and just a square wave with ripple. This is the time domain. And this is just x of t, and it can be in volts, it can be in amps, it can be in unitless. It doesn't matter what the axis is here. This is 0 here. Now, the first thing you have to know about a signal, and most of you do, you have to identify what's called a period. T is called a period. It's the interval over which it repeats itself. How many know that from physics and whatever other courses, your math courses, right? Period is very common. Period is related to frequency, where this is called the fundamental frequency. Is F naught, and that's 1 over the period. So remember that, that's the fundamental frequency. Also, omega naught is something that we use all the time, and that's 2 pi over t, or 2 pi F naught. And most of you know the relationship between frequency in hertz and frequency in radians per second is just 2 pi. This is important. Now, after that, the next thing we talk about is something called the average value. Of the waveform. Average value of x of t. And that's x, and you can call it anything you want. X0, sometimes it's rendered as C0, sometimes it's a bar over the x. It's just the average value. The average value is always the integral from 0 to t times 1 over t of the signal x of t dt. That's all it is. So the average value of anything is just really integrating that function over a period and dividing it by the length of the period. You're probably very familiar with that concept, average value of things, right? The average power, the average, that's just common, right? Now a sine or cosine wave have an average value of 0. Remember that, and that's important to also remember. Got it? So now we're getting into what Fourier series analysis really is. Has anybody had this before, by the way? You have. In what course? Did you have it in DiffyQ? Did anybody have it in DiffyQ? I try to figure out where you get stuff, because I don't know in the mathematics department where they put this. This is a very powerful technique, because we're going to do this. We're going to take waveforms that are periodic waveforms that are fed into circuits, and we'll be able to get the output from for a periodic non-sinusoidally varying, non-sine or cosine varying waveform. And this is so important with circuitry. So what do we do to do this? Well, we say that x of t, it is periodic, can be rendered as some infinite series. Write this down. This is going to be the exponential Fourier series. I can show you how to get the trigonometric out of this, but this is the one people use, in my opinion. It's the one that's really the go-to. You don't mess around with some of this other stuff. It's got some beautiful properties the mathematicians like, but engineers want answers. So here it's going to be the sum from, and you can use n equals minus infinity to infinity. N is an integer value, by the way. times a value, and you can call it C of n. That's a scalar value that we're going to calculate, times e to the j n omega naught t. Now, n's an integer, omega naught is 2 pi f naught, or 2 pi over t, and t is the time. We're going to take x of t and we create an infinite series, theoretically. Now, the question is, how do you get x of n?